Derivative formulas continued. Now that we know the derivative formulas for polynomials, power functions, and trigonometric functions, we want to take a look at the remaining functions that we study in this course, and that includes exponential and logarithmic functions. For exponential functions, let's start with the example 3 to the x. So consider the function 3 to the x. If we want to approximate the derivative at 0, we need to look at the average rate of change really close to 0. So if we go ahead and pick negative 0.01 on the left and 0.01 on the right, we can use average rates of change to approximate the derivative at 0. So here, if we plug each of these values into our function 3 to the x, we get the following outputs. Now, I've elected to keep all of my decimal points, but you can keep them on your calculator or you can write them down. So here, we want to find the average rate of change on the left and the average rate of change on the right. So if we do change in y over change in x to the left, so 1 minus 0.98907400042 divided by 0 minus negative 0.01, I get 1.0986122. And when I do the same thing and I find the average rate of change on the right of 0, I get 1.104669194. Now, the reason I'm approximating my derivative this way, instead of using the definition of derivative, is that if I plugged in an x plus h, I wouldn't be able to manipulate the algebra to simplify it enough to get rid of the h. So instead, I'm using my average rates of change to approximate the derivative at this point. So looking at these two values, I'm pretty certain that my derivative here, f prime of 0, is pretty close to 1.1. It might be something like 1.09, but we can see that it has to be between 1.098 and 1.104. So I'm going to approximate it to be 1.1. Now, if we take a look at the picture of 3 to the x and a picture of the derivative, if we were to approximate the derivative at every value, what we get is the following. The original function, f of x, is in black, and the derivative function for every point is plotted in red. We approximated the derivative at 0 to be about 1.1. So you can see that that red function, the derivative function, crosses through at roughly 1.1. And if we approximate the derivative at the other values of x shown here, so from negative 4 all the way until 1, and you plot those, you get that red line. One thing that we notice here is that the derivative function is very close to the original function. They look very similar, only they're slightly off by a factor. So I suspect that the derivative function is going to be 3 to the x times some sort of constant, which will stretch the y values. Let's look at another picture to see if it helps illuminate anything. Similarly, if we were to graph f of x equals 2 to the x and the derivative estimated at several points, we get the following graph, where 2 to the x is going to be the graph that's in black, and the derivative at every point is the graph in red. Again, we see that it looks very similar in shape and curvature, and therefore we expect that the derivative of 2 to the x to be related to 2 to the x itself, maybe multiplied by some sort of constant. Looking at patterns of exponential functions, we're able to arrive at the following formula. The derivative of f of x equals a to the x, where a is some number, is going to be a to the x times the natural log of a. So that means that we're going to get the same exact function back times the natural log of the base. Let's look at a couple quick examples. So suppose that f of x equals 12 to the x. Exponential functions have a number in the base, and the exponent is where the variable is. According to this formula, I'm going to get the same function back, 12 to the x, but I'm going to multiply it by a constant, and that constant is the natural log of the base. And the base here is 12. So that'll work when the base is any number. Let's go ahead and see what happens, because we're going to have a special case when we look at the function e to the x. So e to the x has a numerical base. E is approximately 2.71. And so when we take the derivative, we're going to get the same thing back, e to the x, times the natural log of the base. But if you remember from algebra, the natural log of e is 1. So that means that the derivative of e to the x is e to the x. That's a special case of this rule, and it's really helpful. We use e to the x a lot. So knowing that the derivative is the same as the original function is a really helpful little trick here. So now we're going to add that to our formula list that we had from before. So currently, our updated derivative formulas list looks like this. We know the derivative of a constant. We know the derivative of a linear function. We know the derivative of a polynomial or power function, sine, cosine, exponentials, and the special case of exponentials of e to the x. Let's do some examples now. Example 1. Use the formulas to find each of the following derivatives. So for the first one, we have 7 to the x. Our formula says when we have an exponential function, we're going to get the same thing back times the natural log of the base. So the derivative is 7 to the x times the natural log of 7. Our next function is e to the x. That was our special case we just talked about. And so the derivative of e to the x is e to the x. 1.2 to the x, again, is going to be an exponential function because we have a number raised to a variable. So we're going to get the same thing back, 1.2 to the x, times the natural log of the base, 1.2. Finally, we have pi to the x. Remember, pi is a number, and so we have a number raised to the x, which is an exponential. So our derivative is going to be the same thing back, times the natural log of the base. So we're almost done with all of the formulas we need to form what's called the basic derivatives. We have one more that we need to add to the list. So let's take a look at this last one. Finally, we need to talk about the derivative of the natural log of x. So the natural log of x has a shape that looks like this. It comes up. It's not defined for negative numbers or 0, so it approaches this asymptote here at x equals 0. And when you graph the derivative, it turns out that the derivative, if you look at every point and you approximate what's happening, looks like this. So when you check these points and you start plotting them and you look again for a formula, what you find is that the derivative is actually 1 over x. So the derivative of the natural log of x is 1 over x. That's our final formula for what we're going to call the basics chart. Now, the basics chart is not called basic because it's easy. It's called the basics chart because it's foundational to the rest of the work we're going to be doing. As our derivatives start to get more and more complicated in the future sections, everything is going to break back down into the derivatives on this chart. So you're going to need to make sure you know these derivatives very well. Take the time to memorize them, to work with them, and to feel comfortable with how these formulas work. Now, in addition to just adding these formulas to this chart, you should also know that the other rules also apply for these new derivatives. So the constant multiple rule will apply. So if we multiply a constant times one of our functions, then that constant will multiply the derivative. Also, the sum and difference rule applies. So if we have functions added or subtracted, we can still take the derivative of each term if some of those are exponential or logarithmic. And finally, the second derivative process is also the same. So to get the second derivative of an exponential or logarithmic function, we'll take the first derivative and then use the same rules to take a second derivative on the first derivative. So let's try some examples. Example 2. Use the formulas to find each of the following derivatives. So for the first one here, we're going to be able to go term by term because again, the sums and difference rules also applies here. So when going term by term, the first term is 5 to the x. We said with an exponential function, you get the same thing back times the natural log of the base. So the derivative of that first term is 5 to the x times the natural log of 5 minus the derivative of the natural log is 1 over x plus, now this last term we have 2 times 3 to the x. So we're going to use our constant multiple rule here. So that means that 2 is going to multiply the derivative of 3 to the x. So we have 2 times 3 to the x times the natural log of the base, which is 3. So our full derivative looks like that. Let's do part B. So the derivative here, again, we can go term by term. The first term here is e to the x. We said the derivative of e to the x was e to the x. 3 times the derivative of the natural log, which is 1 over x. So this last term, just so you know, we could write as 3 over x because we can multiply the 3 into the numerator. It means the same thing. Part C. So here again, we're going to go term by term. And we're going to start with this 10 to the x. The derivative of 10 to the x is going to be 10 to the x times the natural log of 10 plus, now here we have 5 times the natural log of x. So we're going to have 5 times the derivative of the natural log, which is 5 times 1 over x. So finally, for our last function here, we're going to go again term by term. The first term is e to the x, and the derivative of e to the x is e to the x, plus the derivative of 6 to the x is 6 to the x times the natural log of 6, minus the derivative of the natural log, which is 1 over x. Hopefully, you're starting to feel comfortable with this practice. So let's look at another example, and now let's also try some second derivatives within that. Example 3. If f of x equals 2 to the x plus e to the x minus x to the 2/3 minus the natural log of x plus 6, calculate the following giving an exact answer. So we talked a little bit before about this, but exact answer means we're not going to be rounding any numbers. So we're not going to be plugging things into our calculator to get a final answer. So let's start by finding the first derivative. So the first derivative of this function, I can go term by term because they're separated by addition and subtraction. So the first term is exponential. So my derivative is 2 to the x times the natural log of 2 plus the derivative of e to the x is e to the x minus, now x to the 2/3, remember that the power comes down and then we're going to subtract 1 from the power. So 2/3 x to the negative 1/3 minus, now 1 over x is the derivative of the natural log. And I'm going to write plus 0 because the derivative of 6 is 0. 6 is a constant. So just to remind us that we actually took the derivative of that, I'm just going to leave that here for now. And then we want to find the derivative at 1. So that means we're looking for the slope of the tangent line of the original function at 1. And we can find that by plugging 1 into our derivative function. Since we're looking for an exact answer, we are not going to simplify anything. So 2 to the 1 is 2. So I have 2 times the natural log of 2 plus e to the 1 minus, now here if you plug in 1 to the negative 1/3, you get 1. So 1 times 2/3 is 2/3 minus 1 over 1, which is 1. Now the only thing I'm going to do here is I'm going to combine my two constants. So the first term stays 2 natural log of 2 plus e to the 1. And I have minus 2/3 minus 1. So that's going to give me minus 5/3. So my final answer in an exact form looks like this. I don't have to write the 1 power of e. I could just write e and it would be the same thing. But here I'm writing it just so I remember that it's no longer a function and it's now a number. Now let's check out the second derivative. So again, we go back to the first derivative and we want to take the derivative of each term that we had in our first derivative. Now let's start with 2 to the x times the natural log of 2. We have to use our constant multiple rule here because our function, 2 to the x, is multiplied by a constant, natural log of 2. So that means that we're going to take that constant, the natural log of 2, and multiply that by the derivative of 2 to the x. The derivative of 2 to the x is 2 to the x times the natural log of 2. We'll talk about that in a minute. Plus, now the derivative of e to the x is e to the x. Now here, the next term, we have a negative 1/3 power. That's going to come down and multiply the minus 2/3. So that's going to make it a plus, and it's going to be plus 2/9 x. Now we subtract 1 from the power, so x to the negative 4/3. And then finally, we have to deal with this term here, this minus 1 over x. So remember that we can rewrite this as minus 1x to the negative 1. We can bring that x up by changing the sign of the power, which means when we take the derivative, the negative 1 is going to come down to multiply the minus, giving me plus x. And now here I'm going to subtract 1 from the power, so plus x to the negative 2. So here I have my second derivative, and what I want you to notice is that in the first term, I have a natural log of 2 times another natural log of 2, all within that first term. So I can write that as the natural log of 2 squared, because when I plug in a 1 here, I'm still looking for an exact answer. So I'm going to write the natural log of 2 squared, there's 2 of them, right? 1 here, times 2 to the 1, which is just 2, plus e to the 1, right? Plus, now if you plug in a 1 here, 1 to the negative 4/3 is 1, times 2/9 is 2/9. And if you plug in a 1 here, 1 to the negative 2 is 1. So again, the only simplification I'm going to do is going to be to add these two constants together. So we have the natural log of 2 squared times 2 plus e to the 1 plus, now 2/9 plus 1 is going to give me 11/9. So my second derivative at 1 looks like this. Again, if you wanted a numerical answer that was rounded, you could plug this all into your calculator and approximate to a certain number of decimals. But this particular problem wanted an exact answer, so we're not rounding anything, and therefore we are not going to turn our irrational functions into numerical answers. Let's try another. Example 4. Find the equation of the tangent line to f of x equals 2e to the x at x equals 0. So remember, to find the equation of a line, we're going to need a point and a slope. Our point we get by taking our x value and plugging it into the original function. Because again, this is the one point that's shared by both the function and the tangent line. This is where the tangent line touches. So when we plug in 0, we have e to the 0 power. Anything to the 0 power is 1, and 1 times 2 is 2. So that means the point where our tangent line is going to touch our function is the point 0, 2. We also need the derivative at 0, because the derivative at 0 is going to tell us the slope of the tangent line. So to get the derivative at 0, we first need to find the derivative. So our function here is 2e to the x. Constant multiple rule says the 2 is going to multiply the derivative of e to the x, but the derivative of e to the x is e to the x. So again, we're going to have 2e to the 0, which is 2. That's the slope of our tangent line. So putting this together, we have y equals 2x plus b. This is the slope. And then we're going to plug in our point 0, 2. So when x is 0, y equals 2. So that tells me that b equals 2. So the equation of my line becomes y equals 2x plus 2. So the equation of the tangent line that touches at the point 0, 2, it touches the function 2e to the x, is 2x plus 2. Let's do another one. Example 5. Find the equation of the tangent line to f of x equals 3 natural log of x at x equals 1. So again, to get the equation of the line, we're going to need the functional value at 1, and we're going to need the derivative at 1. So the functional value at 1 means we're going to plug 1 into the original function to get the y value. The natural log of 1 is 0, and 0 times 3 is 0. So that means the point where our tangent line touches is going to be at the point 1, 0. We also need the derivative at that point, as that will tell us the slope of the tangent line. So the derivative of 3 times the natural log of x is 3 times 1 over x. Plugging in a 1, we get 3 times 1 over 1, which is going to give us 3. That's the slope of our tangent line. So then we have y equals 3x plus b. We're going to plug in our point, 1, 0. So here we're going to get 3 times 1 plus b. So subtracting the 3 over, I get b equals -3. So the final equation of my tangent line is y equals 3x minus 3. So again, being able to find the derivative is going to help us to figure out the slope of our tangent line, which will then allow us to find our actual tangent line. Let's look at a more applied problem of how these derivatives of natural logs and exponentials might come up. Example 6. When money is invested, it gains value depending on a lot of different things. One of the important factors is how money is compounded, which is how often the interest is added to the principal amount. If the interest is added 1 time per year, we say that it's compounded annually. The equation for annual compounding is given by f of v equals pv times 1 plus r to the t, where fv is future value, so how much you'll have at the end of your investment. PV is present value, or the amount you initially invest. R is going to be the interest rate, and we're going to enter it in decimal form, and time t is going to be given in years. We're going to use this idea to look at some things about money and see how this type of exponential function will relate to the derivatives we're learning. Part A. Suppose you invest $1,000 in an account that has an interest rate of 2.5%. How much money will be in the account in 5 years? There's nothing in this problem that says anything about a rate. In fact, we're just going to be doing a direct computation. If we're investing $1,000, that's a present value, the amount we initially invest. We want to know how much we'll have in 5 years. So that's a future value. So we're going to be using future value equals 1,000, that's our present value, 1 plus r. My rate here is 2.5%. To turn that into a decimal, I write 0.025 to the t, but my t here is 5 years. So my future value can be found by computing all these numbers very carefully in my calculator. So I punch them all in, and my future value on this investment is going to be $1,131.41. All of these examples are talking about money, so we're going to attribute the dollar sign when we talk about the answers. I'm also going to round to 2 decimal places because our currency system allows money to go out to 2 places. Another way to compound money is monthly. So this is something you may see when you go to the bank, a monthly checking rate. That's how typically savings and investment accounts work that are common at banks. That means that once a month, interest is added to your account. However, you do not receive the interest rate each month. You don't get 2.5% every month. Instead, the interest rate's divided up by 12, and each month you get a little chunk or 1/12 of that 2.5%. So the formula for monthly compounding is given by future value equals present value times 1 plus r divided by 12 times raised to the 12 times t. So we're doing r divided by 12 because we're dividing our interest rate into 12 applications. And then, since we're doing it 12 times per year, we're raising it to the 12 times t. So part B, assuming the same initial investment amount, interest rate, and number of years as part A, calculate the future value. Do you expect it to be the same as part A? Do you think it'll be bigger? Do you think it'll be smaller? take a guess. Pause the video, write down your guess, and then we'll calculate it together. So here, plugging in all my numbers really carefully, I get future value equals, now my initial amount is $1,000, and I'm going to do 1 plus 0.025 divided by 12 raised to the 12 times 5. I'm going to carefully enter all these numbers into my calculator. Again, try to be careful with your calculations and your parentheses and things like that. And I'm going to get $1,133, even if I round to 2 decimal places. So it is a little bit more. So by getting my compounding to be done monthly, I actually end up with about $1.59 more than if I had done it annually. And that may not seem like a big deal, but if you're someone who invests millions of dollars, that can add up really, really quickly. So now that we have a sense of the difference between annual compounding and monthly compounding, let's look at some examples of how we're going to apply the derivative. Part C. For each of these general formulas, find a function that represents the rate at which the future value is changing. Keep in mind that t is your variable and PV and R are constants. So let's start with the first function we had, which was future value equals present value times 1 plus R to the t. Since t is our variable, that means if we're going to take the derivative of this function, it's an exponential function because we have a number raised to t. So we can write the derivative like this, f prime of v. Now, PV is a constant, so this is a constant multiple situation. So PV is going to multiply our derivative here, and the derivative of an exponential says we're going to get the same thing back times the natural log of the base. And my base here was 1 plus r. Now let's take a look at the other equation. So our second equation said future value is present value 1 plus r over 12, all raised to the power of 12 times t. This one's a little bit trickier because for an exponential function, the rules we have so far talked about having it raised to t, not 12t or some other constant times t. So we have to do a little creative algebraic rewriting so that we can use our rule. So I can rewrite this function as PV times 1 plus r over 12 to the 12th, all raised to the t. Because remember, if you raise a power to a power, you're going to multiply them together, which means if you have two things multiplied together in a power, you can separate them as a power raised to a power. The reason this is helpful is because this here, 1 plus r divided by 12 to the 12th, right, is going to be a number in itself because r is the interest rate, right? And so all of that is a constant number. So the derivative here, again, FV prime, is going to be PV from our constant multiple. That number is going to multiply our derivative. And we're going to multiply that by 1 plus r over 12 to the 12th to the t. So we get the same thing back times the natural log of the base. And my base here is going to be 1 plus r over 12 to the 12th, because that's the constant part of that function. So we found a way to write the derivative of how quickly our investment is changing, knowing that the variable is t and knowing how to take derivatives of exponentials. For part D, it wants us to explicitly calculate the rate at which each function is changing if time equals 3, present value equals 1,000, and the rate is 0.025. So what we need to do is go back to our derivatives and plug in these values. So here, if we want to find the rate at which the future value is changing, we'll plug in 1,000, 1 plus 0.025 cubed times the natural log of 1 plus 0.025. So we plug in all those numbers, we carefully crunch that number in our calculator, and we get 26.59. And that's going to be in dollars per year. So remember, our independent variable t is time, and time was given in years, and our dependent variable is future value of your money, and so that's going to be in dollars. So that means that my investment is increasing by $26.59 per year when it's been 3 years. Let's do the same thing for our other derivative when we're compounding monthly. So again, we're going to carefully plug in our values. So we have 1,000 times 1 plus 0.025 divided by 12 raised to the 12th, all cubed, times the natural log of 1 plus 0.025 divided by 12 to the 12th. Close the parentheses there. Again, we're going to carefully plug everything in. And when we crunch that number, we get that we're increasing at approximately $26.92 per year. So dollars per year. So again, it's really useful to know how much we're increasing and which one's a better scenario for us. We can see here that when we compound monthly, the rate at which our investment is increasing is slightly higher than the rate when we're annually compounding. So when you go to do your investments, if you have the choice between annual compounding and monthly compounding, monthly is going to get you a little bit more money. And the more money you invest, the bigger difference this makes. And we're able to use derivatives here to figure out how quickly our investment was changing because we were able to calculate the rate of change of an exponential function using our derivative rules.